Welcome to the deep dive. Today we're focusing on just one specific phenomenon from some physics material you've shared. We're setting aside the bigger picture for now and really zeroing in on something that, well, completely shook up physics back then. We're talking about the photoelectric effect.
And it sounds pretty straightforward on the surface, doesn't it? You know, light hits something, electrons come off. Simple.
Yeah, seems simple, but those observations, they held this really deep puzzle that the physics of the time, classical physics, just couldn't crack.
It really couldn't. All those established wave theories,
Yeah.
they just fell short here.
Absolutely. So our mission in this deep dive is to walk you through that puzzle. We'll look at the basics, the experiments, the results that were so baffling.
The ones that didn't make sense classically.
Exactly. And then the breakthrough idea that finally explained it all.
Right.
You know, the birth of the photon. It's all drawn directly from the material you gave us.
It's just a fantastic case study, really. How seemingly simple experiments can force a total rethink of fundamental physics.
Okay, let's dive in then. The basic idea, like the material lays out, is simple. Shine light, or other electromagnetic radiation, onto a metal. And if the conditions are right, electrons get kicked out. That's the effect.
And the material gives a nice, simple visual, like that zinc plate in an electroscope experiment, figure 2.4.
Right, that one. So you take a zinc plate, charge it negatively, put it on an electroscope, and the gold leaves spread apart because they're negatively charged too.
Standard electrostatics.
Yep. Now shine regular visible light on it, like from a desk lamp or something.
Not much happens.
Right. The leaves just stay spread apart. The charge isn't going anywhere.
Okay, but then comes the interesting part. You swap the visible light for ultraviolet light, maybe from like a mercury lamp.
And you shine that UV light on the same negatively charged plate.
And suddenly, the leaves start to fall.
They collapse because that negative charge is leaving the plate. Electrons are being emitted.
And crucially, as the material points out, if you try shining that UV light on a positively charged plate,
Nothing, absolutely nothing happens.
which really nails it down. It confirms that it's specifically negative charges, electrons, that are being knocked off the surface by the UV light.
So, straight away, there's a clue. Visible light did nothing to the zinc, but UV light worked.
It suggests the kind of light matters, the frequency perhaps, not just whether light is hitting it or not.
Which is already a bit weird, isn't it? From a classical perspective, light's energy is in the wave. So surely if you just shine enough wave, intense enough, you'd eventually give an electron enough energy to escape.
You'd think so. Why should the color or frequency be the deciding factor? That didn't quite fit the wave model.
So they needed better experiments to figure this out properly.
Exactly. More controlled setups, like the photocell described in figure 2.5.
Right. Walk us through that. What's the setup there?
Okay, so you've got a vacuum tube important to get rid of air molecules that electrons could bump into.
Okay.
Inside, there's a metal plate, that's the cathode, that's the surface the light shines on. And facing it, there's another electrode, the anode. Its job is to collect any electrons that get emitted from the cathode.
And you can measure the flow?
Yeah, you hook it up to a circuit, you can measure the current, which tells you how many electrons are flowing per second.
And you can also apply voltages, right, between the cathode and anode.
Yes, that's key. Make the anode positive, it helps pull the electrons across. Make it negative,
It pushes them back, it repels them.
precisely. And that repulsion is really useful. If you apply a negative voltage to the anode, a reverse voltage, you can slow the electrons down. If you make it negative enough, you can actually stop even the fastest electrons from reaching the anode.
Ah, okay. And that specific voltage needed to stop all the current.
That's the stopping potential. And it's super important because it's a direct measure of the maximum kinetic energy, the maximum speed, essentially, of the electrons coming off the cathode.
Okay, the setup makes sense. Controlled light source, vacuum, measuring current, using voltage to measure electron energy. But now, the results. This is where things got really weird for classical physics.
Yeah, this is where the crisis really started. These careful experiments gave results that just, well, flat out contradicted the classical wave theory of light.
Okay, let's break down what they found based on the material. First, what happens when you change the intensity of the light, like make it brighter or dimmer?
Right. So you shine light of a certain frequency, one that does cause emission, and you crank up the brightness.
Okay, my classical gut feeling says brighter light means more wave energy hitting the surface per second. So more electrons should get knocked out, and they should come out faster with more energy, right? More push from the wave.
Well, your intuition is half right, according to the experiments, and it's the half that did fit the wave model, sort of. Increasing the intensity does increase the number of electrons emitted per second.
So more current, like figures 2.6 and 2.8a show.
Exactly. Brighter light, more electrons, more current. That part seemed okay.
But there's always a but, isn't there?
There is. Because the experiments also showed absolutely clearly that increasing the light intensity had zero effect on the maximum kinetic energy of those electrons.
Wait.
Look at figure 2.8a again. You increase the intensity, the saturation current goes up, meaning more electrons, but the stopping potential, the voltage needed to stop the fastest ones, stays exactly the same.
Hold on. So if I have a dim green light and it knocks out electrons with a certain top speed, and then I replace it with a blindingly bright green light of the exact same frequency, I get way more electrons. But the fastest ones are still going at that same top speed. That just feels wrong. Brighter light should mean more energy transfer.
It felt wrong classically, too. The wave theory said energy is spread across the wavefront. Brighter light means a more intense wave, more energy density. You'd absolutely expect it to give electrons a bigger kick, more kinetic energy, but nope. The experiments disagreed.
So the energy an electron got didn't depend on the total wave energy hitting the metal. It depended on something else.
Something else entirely. Okay, puzzle number 1. Now, puzzle number 2. The effect of frequency. Remember the zinc plate UV worked, visible didn't.
Right. So what did the photocell experiments show about frequency or color?
This was maybe even more shocking for classical physics. The results, shown clearly in figures like 2.8b, 2.9, 2.10, they showed that for any given metal, there's a minimum frequency required to get any electrons out at all.
A minimum frequency.
Yes, a threshold frequency. Let's call it F, like in the material. If the light's frequency F is below F.
Nothing happens.
Yeah.
Even if the light is incredibly intense.
Precisely. You could shine super bright red light, low frequency, on potassium for years, and not a single electron would pop out. But switch to even a very faint blue light, higher frequency, above potassium's threshold.
And electrons immediately start falling.
Instantly. This completely contradicted the wave model, which predicted that any frequency, if intense enough and shown for long enough, should eventually deliver enough energy to free an electron. But experiments showed this sharp cutoff, this threshold frequency.
Okay, that's a huge problem for wave theory.
Yeah.
And what happens above the threshold frequency? Does frequency affect the electron energy then?
Yes. That was the other key finding. Once you're above the threshold frequency, F0, the maximum kinetic energy of the emitted electrons increases directly, linearly, with the frequency of the light.
Linearly. So higher frequency means proportionally higher maximum kinetic energy.
Exactly. As shown in those graphs, like figure 2.9 and 2.0, the higher the frequency of the light you use, as long as it's above threshold, the fastest electrons come out.
So, wait. Intensity controls the number of electrons. But frequency controls the maximum energy of the electrons.
You got it. Totally backward from classical wave expectations where intensity should have controlled energy.
Mind blown. Okay. And this threshold frequency F0, is it the same for all materials?
No, and that's another important detail the material highlights. Different metals have different threshold frequencies. Table 2.1 shows some examples. Sodium needs a lower frequency than zinc, for instance.
Which means it's easier to knock electrons out of sodium than zinc. Takes less energetic light.
Exactly. It depends on how tightly the metal holds onto its electrons.
Okay, one more piece of the puzzle. Timing. Classically, maybe an electron needs time to sort of soak up energy from the wave, especially if the light is dim.
You might think so, like filling a bucket slowly with a trickle of water. But the experiments showed something else entirely.
What?
The emission is practically instantaneous. The material mentions it happens within nanosecond, 10 euroseconds, as soon as light of sufficient frequency hits the surface.
A billionth of a second.
Yeah.
Even for really faint light.
Even for faint light, there's no measurable lag time for the electron to accumulate energy. It either gets enough energy to escape right away, or it doesn't escape at all.
Okay, let's recap this experimental nightmare for classical physics. We've got 1. Max electron energy depends on frequency, not intensity, classical theory. 2, there's a minimum threshold frequency for emission. Classical theory, couldn't explain. 3, emission is instantaneous. Classical theory predicted a delay.
Yeah, it was a complete breakdown. The wave theory of light, which worked so beautifully for things like diffraction and interference, just could not explain these basic facts about how light interacts with electrons in a metal. Physics was in a bit of a crisis.
So how did they get out of this mess? There must have been a new idea.
There was a truly revolutionary one, proposed by Albert Einstein in 1905, building on earlier work by Max Planck related to black body radiation.
Okay, what was the big idea?
Einstein proposed that light energy doesn't actually travel as a continuous, spread-out wave. Instead, he suggested light energy is delivered in discrete, concentrated bundles or packets, little lumps of energy.
Packets of light energy, not waves.
Well, behaving like particles in this interaction, these packets were later called photons.
Photons. Okay, so light is made of particles.
In terms of how it delivers energy in this effect, yes. And the crucial part, borrowing from Planck, was that the energy of one single photon is directly proportional to the frequency of the light.
Ah, frequency is still key. And that's the famous equation, E equals HF.
That's the one. E is the energy of one photon, F is the frequency of the light, and H is Planck's constant.
Which the material gives as 6.634 times 10 to the minus 34 joule seconds. Tiny number, but fundamental.
Absolutely fundamental. It connects the particle-like energy packet, E, to the wave-like property, F.
Okay, intriguing idea.
Yeah.
But how does thinking of light as these energy packets, these photons, suddenly explain all those weird experimental results?
It works beautifully. Think about the interaction now. It's not a wave washing over electrons. It's like collisions. One photon hits one electron.
A one-on-one interaction.
Exactly. The electron absorbs the entire energy of that single photon, HF. All or nothing.
Okay.
Now, for the electron to actually escape the metal, it needs a certain minimum energy just to break free from the forces holding it inside. That minimum escape energy is called the work function of the metal. Let's call it A phi.
The energy cost to get out.
Right. And the material connects this directly to the threshold frequency we saw. The work function energy is equal to H times F, the threshold frequency, HF euro.
Got it. So what happens when a photon hits an electron?
Okay, case one. The photon's energy, HF, is less than the work function.
Not enough energy to pay the escape cost.
Right. The electron absorbs the photon, gets a little jolt, but it doesn't have enough energy to break free. It stays inside the metal.
Ah, and that immediately explains the threshold frequency. If F is less than HF, then HF is less than HFY, which is big way. So no electron can ever escape no matter how many photons hit it.
Exactly. It doesn't matter how bright the light is, how many photons per second. If each individual photon doesn't have enough energy, HFA, none of them can liberate an electron. Threshold frequency explained.
Okay, mind's still blown, but it makes sense. What if the photon does have enough energy, if HF is greater than or equal to A?
Then the electron absorbs the photon's energy, HF. It uses exactly all amount of that energy to pay the escape cost and break free from the metal surface.
And whatever energy is left over.
That becomes the electron's kinetic energy, K, once it's outside. So the kinetic energy is the photon's energy minus the escape cost. K equals HFA.
K equals HF minus phi.
And since the work function is equal to HF air, you can also write it, as the material does, as K equals HF HFA. The kinetic energy is the photon energy minus the threshold energy.
And that's the maximum kinetic energy, right? Because some electrons might lose a bit more energy on the way out.
Precisely. Some might be deeper in the metal or have collisions. So Kmax describes the energy of the luckiest electrons, the ones that escape most efficiently.
Kmax equals HF HF here.
Wow.
That one equation. Does it fix everything? Let's check.
Let's do it. Puzzle 1. Max kinetic energy depends on frequency. F, not intensity.
Well, Kmax equals HF HF here. There's F right there. Kmax increases linearly with F. Intensity isn't in the equation at all.
Perfect match with the experiments. Figures 2.9, 2.920, the energy comes from one photon, and that photon's energy depends only on F.
Okay. And intensity controlling the number of electrons.
Yeah, that fits too. More intense light just means more photons arriving per second. If each photon has enough energy, H, F, F, H, F, evo, then more photons mean more successful one-on-one interactions, more electrons getting knocked out per second, more current.
But each electron still only gets energy from one photon, so their max energy doesn't change with intensity. Makes sense.
Yep. Puzzle 2, the threshold frequency, F.
Solved. You need HF to be at least HF, or A, to get any kinetic energy out. Kmax is 0, so F must be up FA.
Exactly. And different metals having different F values, that just means they have different work functions, different binding energies for their electrons, which makes perfect physical sense. Sodium's work function is about 2.4 eV, zinc's is 2.9 eV, according to table 2.1.
Okay, and puzzle 3, instantaneous emission.
Also solved. The interaction is one photon, one electron, one instant. The electron absorbs the photon's energy essentially all at once. There's no need to wait and accumulate energy from a spread out wave. If HF escape happens immediately,
It's really elegant. One core idea, light energy, comes in packets called photons, with EF just unravels all the experimental mysteries.
It really was a landmark achievement. It showed that light, which everyone knew behaved like a wave, also had to behave like a stream of particles in this context.
And the material mentions the unit electron volt, EV. Just quickly, what is that again?
It's just a convenient unit for these small energies. 1 electron volt is the energy an electron gains when it moves through a potential difference of 1 volt. It's equal to about 1.6 times 10 Nordhole joules. Work functions are typically a few eV.
Okay, so stepping back, why is understanding this specific effect, the photoelectric effect, so important beyond just physics history?
Well, first, it was absolutely crucial evidence for the particle nature of light. This idea that things can be both wave-like and particle-like, wave-particle duality, is a cornerstone of quantum mechanics.
Quantum mechanics is, well, it's everywhere in modern technology.
It really is. Anything that turns light into electricity often uses this effect or something very close to it. Solar cells.
Photons hit silicon, knock electrons loose, create current. Photoelectric effect.
Exactly. The sensors in your digital camera or phone.
Tiny pixels collecting photons, generating electrical signals based on light intensity. Photoelectric effect again, basically.
Even older things like photomultipliers used for detecting really faint light rely on it. It's fundamental to how we electronically sense or harness light.
So it's not just some weird lab curiosity. It's powering our devices, our green energy.
Yeah.
It's built into the modern world.
Absolutely. All because of a puzzle about electrons getting knocked out of metals. It forced a revolution in understanding light.
Okay, let's sum up this deep dive then. The photoelectric effect. Electrons ejected from metal by light. The experiment showed things classical wave theory couldn't explain. Max electron energy depends on frequency, not intensity. A minimum threshold frequency is needed, and it happens instantly.
And the explanation came from Einstein's photon concept. Light energy arrives in discrete packets, photons, with energy EAF. An electron absorbs 1 photon. If HF is greater than the work function, or HF, the electron escapes with maximum kinetic energy, Kmax, equal HFA. This explained everything and established the particle nature of light.
A huge step towards quantum mechanics and this idea of wave-particle duality.
Which leaves us with a bit of a mind-bending thought, doesn't it? We found out light acts like particles here. Other parts of physics show that particles, like electrons, can act like waves. So this neat division we make between waves and particles in our everyday world, maybe it's just an approximation. What if, deep down, everything has both waves and particle aspects, and we just happen to notice one or the other depending on how we look? What other seemingly solid parts of our reality are secretly quantum underneath?
A profound question to ponder. And it all started with light hitting metal.